IP, and his call sign, of course, as he's put on his note there, is also G5BMH, because he also holds a UK call sign. I'm just also going to say hello now to viewers on YouTube who are now live on YouTube as well as on Zoom. So good evening to those of you watching on YouTube. Can I, by way of introduction, just introduce Rick in a couple of words, really. Rick, like many of us, started his journey on amateur radio as a young man, in Rick's case, playing with a crystal set. And then discovering these guys talking apparently on the radio. In those days, of course, radio amateurs used AM because we're looking back now to the 1950s. And Rick asked his dad about it, and his journey into amateur radio began as a shortwave listener, as it's done for quite a few people in this room. Rick was first licensed in 1962, I believe, Rick. In the US, and then moving to Germany to get his German license in 1972, and then later on getting his UK license as well. Rick is, I think, as I've said before to people here, is a founder of Spider Beam US, the company that makes the Spider Beam antenna used by so many people, including Denby Dale Amateur Radio Club. And if you look very carefully at the picture behind me on the screen here of one of our field days a couple of years ago at Farnley Tice, you'll see sticking out of my head just at the top there, the Spider Beam, the club Spider Beam that is used from time to time. Rick is also the founder of the Aerial 51, making lightweight antennas and at one stage high specification transceivers as well, and has got a lifetime of amateur radio activity, contesting a particular interest of his, as you'll find out in a second. So Rick, you and I came to meet each other through talking about the off-center fed dipole, and I was wanting to find out more about the issues about building off-center fed dipoles, how they worked, the problems with them, and how they could be made better. And I came across you and came across your websites and thought, here's someone who's got a wealth of information that really needs to be given a platform. So Rick, I'm going to pass the microphone over to you and hand over to you to take the mic and take us away this evening.
Okay, it says unmute myself.
Now you are unmuted. You are unmuted, Rick. Yeah, you're fine.
Well, guys, I worked 35 years in IT as a technical marketing manager, gave lots of presentations, but never one like this. You know, back then you carried along slides or you could shoot with a beamer, and the people we were talking to were close enough that you could see the whites of their eyes. And the last time the Brits and the Yanks could see each other's whites of the eyes, I think they were shooting at each other. So we will not be shooting tonight. So so I hope I don't click anything wrong. And every now and then my internet fails. So if I disappear, I'll be back in 2 or 3 minutes, something like that. So, and thank you, Nick, for inviting me. The only thing is, if you had told me I have to do this one day after Emil gives his presentation, I'm not sure I would have accepted it. I would have said, can we wait a week or two? It's a hard act to follow. So I'm very enthusiastic about wire antennas, always have been. Not as enthusiastic as Emil is about his rock climbing and his activities and all that. So let's see, I just clicked something and nothing happened. There we go. My ham history is all posted. I didn't want to get into a long dissertation on that. It's posted on one of my websites. I have 3. All of the links are at the very end, the last slide, as well as a dedicated email address for questions. So I'd like to get going. At the moment, I've got the menu blocking my view of my screen. Okay, in part 1, it's about what is OCFD and how good are they? Why not OCFD? A lot of people hate them. So what are the alternatives? Why does OCFD have a shady reputation? Is it accurate or not? And this is one extra for you guys in the UK, at least, the Balun, to be or not to be. how can the OCFD work multiple bands without any traps or tricks or anything like that? And why does it not work 15 meters? Show you some tricks for making it work. Once we understand why it doesn't work 15 meters, you'll see how easy it is to make it work on 15 meters. But now here's the kicker. I'm in several groups. Some of you are in the groups with me, different groups in Facebook or Groups.io about antennas. And we're always hearing people say, I've built this or I've built that, and it works. And they list maybe 3 stations that they've worked. And they consider that work. And, you know, that's sort of that's open for discussion. You know, what is the difference between work and work right? And I plan to give you my view of that. And the most important part is not tonight. That's going to come in the next presentation, and I think it's about 3 weeks. And once we go through all the technology, then it'll be easy to understand why I do things the way I do, why I build the antennas the way I build them. Before we get going, I've got the menu again blocking my part of my screen. But anyway, this presentation uses abbreviations, and the reason you can't talk about OCFD antennas without talking about common mode current, and that's just too long to write out on every slide. So I abbreviated it CMC, which, you know, some people don't like, but so I define that this is RF flowing on the outer surface of the coaxial shield. The confusion is the acronym CMC elsewhere often means common mode choke. Well, I'll talk about the common mode chokes as well, but I'll just call them chokes. And if I write CMC, I mean common mode current. More important, I think, is common mode impedance. This is the measurement in ohms of the ability of an RF choke or a balun to impede the flow of common mode current on the feed line. And the final term, this is one I invented, SWR min, and what I mean is the frequency at which we have minimum SWR, you know, on each band. And writing all that out was a mouthful and, you know, half a screen full. So I just came up with the term SWR min. It's stated in megahertz, you know, so I don't mean, you know, 2 to 1 or 3 to 1. I mean, you know, 3.562 kilohertz or something like that. The last one should be apparent. I use ATU, and you know, I like to say antenna matchbox. That's what we called them 60 years ago. Today, most people say antenna tuner or antenna tuning unit, all the same. I abbreviated ATU because, once again, I don't want to write out long words. Now, a lot of what I tell today is going to contradict what you've heard or read or even done yourself. And I've got a reason for doing it differently. And when I first put my presentation together, it was about 3 times as long as it is now. So I had to shorten it. So I took a lot of the information, which is basically just backup information with links to the people I call gurus like W8JI and VK10D and G3TXQ, etc. And if I have a page where I'm talking about technology and I don't want to go too deeply into it, I'll put this little yellow embedded in yellow link sign, which means if you go to the link page, and for part 1, it's this URL. If you get the PDF, this should be active. You should be able to click it and go to it. So you go to that page, find slide number 3, and there you'll find the whatever information I added in to back that up. The next thing I like to do is quote a very, very famous American who lived 180 years ago. He speaks my kind of English because I'm from down south. It ain't what you don't know that gets you into trouble. It's what you know for sure that just ain't so. So some of, if not a lot of what I talk about today is, like I said, it's going to contradict what you have learned elsewhere on the internet. And I'd remind you, it's the same internet that claims that John Lennon is alive and living together with Elvis on a side street near Piccadilly Circus, you know, so you can find just about anything. And the trouble is with baluns and OCFD antennas, a lot of what we find just ain't so. Now, if he was alive today, Mark Twain would just say this is fake news. Basically, I'd warn everybody to be very careful in trying to learn about baluns on the internet. Be careful to use reliable sources. These are the sources I used while I was learning. These are in alphabetical order. No particular order. The only thing is, if you're starting out and learning, I highly recommend this. And like I said, the links, you go to the page supporting this slide, and you'll find links to the webs or blogs of these different guys. But this is a good place to start. Roy Lewallen actually, is it balance what they do and how they do it. And you're probably all familiar with the term voltage balance and current balance, and those terms did not exist before he wrote this document. It was published in the ARRL Antenna Compendium, Volume 1. And every year at Dayton, he gives a presentation on balance. And so if you really want to learn what they do, you should read this. Now, if you think you know pretty well what they do, you probably ought to read it again. And if you know for sure what they do, then for sure you ought to read it again and make sure that you know for sure, because, you know, it's what you know for sure that just ain't so. It gets you into trouble. So, like I said, all of these, I think every word these guys have ever written, I've read 3 to 5 times in my long path to learning what I learned about the balance and the OCFD antennas. First of all, what is an OCFD antenna? Well, you know, I think most people have a vague idea of what it is. It's a dipole. It's a half wavelength long, coax fed. It's the successor to the single wire Wyndham antenna, to the original. That was 1928. It's a half wavelength long on its lowest band, and it's fed somewhere between its center and one end of the antenna. How well does it work? Well, for many years, I thought these were lousy because I built a single wire fed Wyndham in 1963, and I played at it again in 72 with a coax fed, and I wasn't happy with the antennas. But then at one point, and I'll come to that in a minute when we look at my QTH, and you see why I had to switch to the OCFD antenna. So after I got mine perfected, a friend of mine was going to work the IOTA contest in 2015. Let me get my mouse down here. I loaned him an Aerial 51 model 807UL. The 807UL is not, so first of all, let me say Aerial 51 does not build the antennas. We do not sell the antennas. We're just 3 guys that play with antennas. Spider Beam has chosen to build and sell some of my antennas. And the 807UL is not in the program, but the 807HD and the portable one, the lightweight one, 807LR. So Paul took along a K3, my antenna, and a 12-meter fiberglass pole. He entered the class Island Expedition class single op running 100 watts, and he took first place overall worldwide. Another friend of mine in the States, Barry, N1EU, I sent him an Aerial 51 404UL when I first designed the antenna, and he used it in the Take It to the Field QRP contest. We don't know this contest over here, but over on their side of the pond, North America, South America, that's quite a popular contest, and Barry took first place overall of all the operators. So, you know, I'm not saying they did it because of my antenna, but they certainly did it despite my antenna. You know, I mean, you can't do it with a bad antenna. He probably could have done it with a couple of other antennas, but you can't have a bad antenna and win a contest like that. But now, how well does this work for me? This is my beautiful QTH, and I call it Ham Hill. And I was living in the States, as Nick said, I founded Spider Beam US. Actually, I moved over there from here, founded Spider Beam US. And after 4 years, we were ready to come back, and I got someone that would take over my company for me. My ex-YL came home ahead of time. She was house hunting, but I actually found this location. I found it in the internet, looked at it on Google Maps, sent her over. She looked at it. She said, "Honey, it's beautiful." I said, "Yeah, but you know, we're renting. We didn't buy it. And we live here where you see the open window, and the landlord lives just above us." I said, "You got to get in writing permission for an antenna." And she got it. And I said, "Well, sign the lease." Of course, in Google Maps, you don't see mountains. And I was shocked when I got here to see the mountains all around me. I thought, I'll never get out of this place. And my antenna, my 80-meter OCFD antenna, which wasn't my first, but it was mounted here. And you can see to shoot stateside, I've got like about a 60-degree angle, and towards Japan, about a 40-degree angle or something like that. Now, I've got a pretty good shot to the south, but, you know, Actually, that's where I need a mountain because the Italians are so loud, but the mountains are in the wrong place. So I'm a contester, got on the air with my OCFD antenna, which was the second antenna I put up. Come to that in a minute. Here's a couple of years results. Lost the logbook here. I don't work so many hours. I didn't back then. 30 hours. That was my best year. If you've ever worked CQ Worldwide and you don't have a beam and all you have is wires, scoring 1,000,000 points is a bit difficult. And that was my best year. The next year, I didn't have time for the CW contest. The XYL had other plans. And just take a look at the run rates down here. So every 1.4 minutes, I had a QSO for 30 hours continuously, and every 5 minutes, a new country. So how does it work on QRP? And I love to work QRP. As Nick mentioned, for a short period, actually for about 4 years, I arranged a deal between a company manufacturing these antennas and Spiderbeam themselves to sell it. And at the time I was working for Spiderbeam. And so we were selling these little radios. I think I said antennas, these little radios. And I was using the little 5-watt radio and a, Aerial 51 antenna, the 80-meter OCFD, 15 hours on the air. These worked 54 countries on 80, 60 countries, actually 61, but I messed up a call sign on one. So, it's not proof that you have the greatest antenna going, but it does prove that it's not bad. And if you look at the run rates again, every 1.7 minutes was a QSO and every 6 minutes was a new country. So it does work pretty good. And most recently, last month, there was a group of guys from my contest club. We're operating East Timor. The last day they were on the air, I thought, well, I better go work them or else I'll miss them. So I got on at about 10 o'clock at night and took me 10 minutes to work them, but I was running 500 watts. So it's not proof that this is the greatest antenna in the world, but it proves that it isn't bad. Now, I said I didn't have my OCFD as a first antenna. This is on the right here. This has always been my favorite multi-band antenna. I call it a double ZEP. Some people call it a doublet. It's a dipole, usually cut for the lowest band and fed with 300 ohm, 450, 300, whatever you have, and some kind of tuner. Keep it simple. Works all bands. You just have to use the tuner all the time. I showed you our house before. The antenna worked great, but the bad news was the feed line ran through the air right past the picture window of the living room of my landlord. And after about 2 days, he says, that's got to go. So I had to take it down and find something else. But what do you take? I wanted an all band antenna. I wanted to contest. I'd love to have one with no antenna tuner. So I started searching, and these were the factors. It's subjective, obviously. Does it need a tuner? How much does it cost? How much space? Weight? Since I use fiberglass poles because I get them for free, then I was looking for something that wasn't too heavy, good reliability. It doesn't matter to me much about aesthetics, but if you have a landlord and XYL and neighbors, it matters. And complexity, I believe in keeping it simple. So I've got a few antennas I looked at. These ones outlined in red, I call contraption antennas. The more gain, I didn't look at it very long. Trap dipole, well, it's got trap built into contraption, so that's practically the epitome of a contraption. This is a good, on the top right, the fan dipole is a good antenna, but as soon as you want a whole bunch of bands, it's kind of a contraption as well. And by the way, as it's pictured here, it does have a gotcha. This slide was borrowed from Martin with his permission, DL7ZB. And I've got actually on this linked page, a document where I examined all of these antennas, wrote lots of details, and then tried to be subjective in the advantages and disadvantages of each antenna. It ended up being a document 19 pages long, so you might not want to read it, but it does go into quite a lot of detail. Now, here's a couple of antennas that aren't so bad. I used this 50 years ago. I had a beam, so I only needed 80/40. It worked well until the traps waterlogged. So I said, well, traps really aren't the thing. I've never used the G5RV or the ZS6BKW, and if I were going to, I'd use the BKW. The reason was, if you go to all this trouble, you may as well just run it a little bit longer and run the wire all the way to the shack. Just use a matchbox. Now, here's my least favorite antenna, and I would never use one, and for some reason, the entire internet seems to think this is the berries these days. Everybody's talking about in-fed antennas. I wouldn't have one. You've got CMC issues. You've got some other problems with it. And by the way, if I absolutely had to feed this antenna or any antenna off of its end, there's a better choice. It's called an in-fed off-center fed dipole. In-connected off-center fed dipole, ECOCFD. Friend of mine published an article on this in Radcom about 5 years ago. It's a Rob M0RZF. He didn't call it that. It's something about an in-fed Wyndham or something was the name of it. 2018, it was in a Radcom issue. And if you really want to find it, and if you write me, send me an email, I'll look up the issue and you can look it up. So like I said, those were all the things I looked at, but they're all complicated. And I like this, keep it simple. So I took another look at the OCFD antenna. It's just a wire with a balun in it. You cut it open somewhere, you insert a balun. But why had I had bad luck with it before? I mean, I had the Fritzo FD4, and it was always down about 2 S units over any dipole I compared it to. The first thing I'd like to say, and no matter what you do, you must choke the OCFD antenna. And I don't care what balun, unless you use a very special new type of balun called a hybrid balun, which has a choke built into it. You should always use an external choke. And we'll look at why that is a little bit later. And it's one of the biggest mistakes most people make when they build them is they don't do that. So this is the classic shown here. It's approximately to scale 1/3, 2/3. Overall length is it's an 80-meter dipole. This one was. And it works 80, 40, 20, and 10. A lot of people say, hey, it works even harmonics. And there's even some manufacturers, balun manufacturers, they claim this does not work on 17 or 12 meters. That's absolutely wrong. This is an outstanding antenna, low SWR. It's a good performer. This antenna works in those bands. What it does not work is 30 or 15 meters. So, I mean, it looked really great, but as a contester, I got to have 15 meters. I mean, without 15 meters, you can't work a contest, really. At least you can't win. So the question was, why does it not work 15 meters? And well, the first thing you'd notice, 1928, when the original Wyndham was designed, 15 meters wasn't even a ham band, so obviously, but they weren't even really looking for multiband performance. They were looking for something else. But, there's obviously some technical reasons why it didn't work, and you got to find them. So the next thing I want to look at is where did the OCFD get its shady reputation from? So, there's some people swear by it, others swear at it. Some people think it's the greatest things in sliced bread, and others say, hey, it's a dummy load, it's a TVI generator, harmonic generator. What's the truth? Well, it's installation dependent. And I got into a bit of I don't want to say argument, but Tom WHAI, he disagreed with this, but I'll tell you, I've not actually had mine over a metal roof, but I've done this before, and even worse. We've all learned you should always run your feed line perpendicular to your radiator. You can't always do that. Sometimes you do have to run it, skewed off to one side. And that's when you start to get into trouble with OCFD. And if you don't have the world's best balun and a choke, you can get into some serious problems. And I'm certain you're going to get into that problems with this as well. So the fundamental problem is this antenna is so susceptible to common mode current, and much more so, far more so. And by the way, I've measured this, and I've got posted on website measurements where you can see the difference. We'll look at a couple of things. And if you don't have a perfect installation and a great balun, you can get into trouble. You can have a less than perfect, but it really must be a good balun. Here's the second problem. All of the manufacturers, almost all, there's a couple of exceptions, but very few, are running single core 4-to-1 Guanella baluns. At least they think they're running a balun. Actually, this is not even a balun. It's just a transformer. Why that is has been explained in detail by G3TXQ on his website, by WHAI, by VK10D on his blog. And I can even show you my measure results, which prove that it does not work. It's just not suitable. The simple fix, of course, to these problems is just use good balun and choke technology. Unfortunately, I don't know of any commercial vendor that's doing this well enough. I know two that are building pretty good hybrid baluns that sometimes work, but not always. And of course, the Spider-Beam one does. I designed it and it works like I designed it. Been tested by a German magazine. You can read the magazine article in English on my website. So until the OCFD manufacturers do their homework and fix these baluns, they're never going to get the antenna right. An easy solution is do it yourself. And this is easier than you think. The biggest problem everybody says they have is the balun. And it seems like everybody is scared. Okay, I learned yesterday from Emil it's allowed to use this word. I wasn't sure, but they're scared shitless to build their first balun. I was too. You're afraid you're going to mess something up. You're not going to get it right. It isn't going to work right. So I never met anyone in my life that was not afraid to build their first balun. And likewise, I never met anyone who was afraid to build their second balun. After they did it, they laughed at themselves. It's so darn easy. And we'll learn how to do that, but it's going to be in part 2. Okay, let's look at common mode current for a moment. If we take a half-wave antenna, if I can find my mouse, half-wave antenna, a dipole on any frequency, any band, and we feed it dead center, this is the point where you'll have minimum problems with common mode current, especially if you run your feed line 90 degrees, perpendicular to the antenna. And when we move off center towards the end, the farther away we go, the worse tendency to generate common mode current there is. And though it's absolutely worst at the end, and this is why I don't like end-fed antennas, end-fed half-wave antennas. Quarter wave is a different story, but end-fed half-wave antennas. So why do they even exist? Well, they were called a Hertz antenna and then a Marconi antenna, and they were used on Zeppelins. And when you're flying about in a Zeppelin, it's about the only kind of antenna you can put out there is a trailing piece of wire. But I don't know any hams that fly Zeppelins, so I don't see why they insist on using end-fed antennas. This text just says what I just told you. So let's move on to the next. What really happens? Why does the antenna perform so poorly whenever it has common mode current on it? And the reason is when it has common mode current, the feed line becomes part of the antenna and dirty things begin to happen. And contrary to what some people think, that's not my mother-in-law. Anyway, the expected antenna characteristics are distorted and skewed, and they can be severely distorted. The frequency of minimum SWR shifts. It usually shifts upward, and it can shift several hundred kilohertz upwards. The level of minimum SWR changes. It can get better or worse. Both change when you change the length of coax. And this is the kicker. You build an antenna at home, you tune it, and if it has common mode current on it, you think it's tuned for resonance or actually for SWR minimum. Then you take it someplace else to the field and it doesn't work like it did at home because you changed the length of coax. Sometimes you even lose coverage of a single band or two bands. And you'll have RF on the feed line. I think everybody knows that or has experienced it. And it can radiate all the way to the shack. I'll show you in another few slides just how strong that can be. The chassis, the mic, the key may all be hot. At a very early age, 50 years ago, I switched from a metal mic to an all-plastic mic for this reason. So I used for many years a Shure 444, all plastic, and that cured the hot lips problem. But I've also had problems with circuit breakers, especially in Tintec power supplies, circuit breakers tripping to fault, and consumer products in your house may be affected, and your neighbors may soon be pounding on your door and they won't be bringing champagne. So the next thing, I have to scroll back up to read the top because I've got a little menu up here covering my top line. Okay, there's two types of balance with significant differences. Oh, and by the way, I am sort of fighting off a cold and my voice is kind of scratchy. That's why I keep drinking tea. So we have two types of balance, and I guess everybody knows this. Maybe we haven't called them that, but you'll recognize them. The transmission line balance, it's a one-to-one balance. Now, I don't know if I can find myself here. This would be a typical one, like here, this, just a toroid with a coax wrapped around it. That's a transmission line balance. The transformer balance, of course, transforms the impedance ratio, 4-to-1, 9-to-1, 49-to-1, etc. Now, with these transformer balance, again, like this, the good news is you have a coax coming in one side and out the other, and the power is transferred, or the energy is transferred just through the coax, inside the coax. It's a wired path. With the transformer balance, it's transferred via flux coupling between the conductors, from input to output. So the balun core is at least partially involved in the energy transfer, and you always have some loss. Now, all of the info on this page is taken directly from Tom Rauch, WHAI, from his page. Suggest you read that. This is just the highlights. The good news with the transmission line balun, because everything is just flowing right through the coax inside, it's hardly affected by the amount of power, nor by a mismatch. Unfortunately, transformer balance, power and mismatch range limited by magnetizing forces to the core. So, and this is how Tom summarized it. By the same size and quality of material, transformer balance handle less power into matched loads and significantly less power into mismatched loads than transmission line balance do. So keeping that in mind, we're going to look at the ideal. Sorry to run it up and down, but like I say, but I can't get rid of this menu here. No, I don't know how to get rid of it. So it always blocks my title, my slide title. Okay, anyway, the OCFD balun must perform two tasks: transform impedance and impede the flow of common mode current. And by the way, the one on the right, this is the primary. This is secondary. If we look at the transformer balance, taken from what we saw on the previous slide, first of all, they have only moderate CMI. I'll show you why that is actually in the next slide, but they have moderate CMI compared to the transformer balun. Oh, excuse me, compared to the transmission line balun. These work best with low permeability, but we need high permeability to get high CMI. So it's, it's counterproductive there to use it. But here's the important thing. The CMI degrades when the SWR rises. Well, we don't always have perfect SWR with an OCFD antenna. And so if you have higher SWR, the CMI degrades, and then more common mode current starts to flow. And that warms the core. And as it warms the core, the CMI degrades, and you have more common mode current, and you can eventually get thermal runaway. Not so with the transmission line balun. First of all, the transmission line balun has twice as much common mode impedance as a similar transformer balun. You'll see why when I show pictures of these on the next, or drawings. These maintain their CMI even when you have high SWR. You don't lose common mode impedance. And you can use a high permeability without endangering the toroid, because power flows inside the coax. It does not use the core for the transfer. So the bottom line is we've got two tasks, and there's no reason to try to do them both with one single balun. Let's do them with two. And you're going to be maybe amazed, but this is actually, where's my camera? If I can get this thing into view, this little guy here. This was the other one that I showed you before. And it's hard to get them both into here. And it's quite a bit larger. This is what a lot of the commercial balun vendors use. Nevertheless, customers continue to burn those baluns up, even though they're much larger. And with my little one here, well, Spider-Beam rates it at 600 watts. That's SSB and CW. And there's lots of users I personally know that run a kilowatt through them. This tiny little things here, but it's designed properly. If you design them wrong, then it doesn't matter what size they are, they're going to burn up. So the main problem is the balun, and as I said, almost all commercial OEMs are building these wrong. They don't understand the unique CMI requirements of the OCFD antenna. I did a field test in 2013. It lasted 3 weeks. To prepare for that, a lot of people, some of you might know, helped me. G3TXQ was very helpful. G3UNA was very, very helpful. In fact, he kind of held my hand every day by telephone and email. And he was friends with Ian White, GM3SEK, and Ian gave me lots of information to prepare for the test. I made 500 measurements, and we're going to look at a couple of them in a moment. But what I discovered was the common mode current problem with OCFD antennas is like 95% on its fundamental. And whenever you go to the higher harmonic bands, it just suddenly falls off dramatically. You don't need anywhere near the common mode impedance on the higher bands that you need on the fundamental. So you don't have to build a broadband balun. You have to build a balun that has a lot of common mode impedance on the fundamental band. This is what the OEMs, the vendors, failed to do. So some of them, though, they don't even understand how the 4-to-1 Guanella balun works because they're still building baluns that don't work right, the single core. But as I've written here, in my opinion, it's not their fault, and you're going to be surprised to see what I put up next. Now, Jerry Sevick has written W2FMI, an outstanding book over baluns. It's basically about how to build baluns. The book is excellent. It has a couple of mistakes and a couple of serious mistakes in it, and this is one of them. He shows us 2 ways to build a 4-to-1 Guanella or current balun, but only one of them works with HF antennas. And the kicker is with HF antennas. That's what he left out. That's what he failed to say. Now, Jerry worked for Bell Labs, and all of his work was done on networks, and the networks were floating, completely ground independent. Well, HF antennas are not ground independent, and this is explained very well in detail with lab measurements and mathematically by G3TXQ, WHAI, VK10D. They all go in and tell you about this and tell you why it doesn't work. Yet almost every balun vendor out there is selling these things. And that's one of the biggest problems. So bring in the 2 dots there. These baluns, basically the single core, they're just transformers because they don't have any common mode impedance at all. Absolutely zero. And in the, I should have, yeah. In the details page and commentary page, I've got links to, there's a good document from G3TXQ where he shows actual measurements and proves this thing has absolutely zero common mode impedance. And the antenna, probably the biggest antenna in the world that needs a good balun, this is the worst balun you could possibly use. And this is what many of the people selling them, especially on eBay, this is what they're using. That's where the bad reputation comes from. So the linchpin to success or failure, it's the balun. And with few exceptions, the 4-to-1, the dual core 4-to-1 Guanella balun, it doesn't have enough CMI to impede the common mode current. And the reason is what I said earlier. It has only half as much CMI as a 1-to-1 Guanella or a 1-to-1 current balun. Now, there's a few exceptions, very few, where that's enough, but most of the antennas we're going to want to build, it's not going to work by itself. Simple solution, of course, would be to use a choke. It's a bit more detailed than that, and we go into detail in part 2, all about what material to choose and why that one and why not something else and how many turns of this or that. That's all in part 2. If you use a 1-to-1 choke balun together with your 4-to-1 balun, you're going to be okay. Even if, I shouldn't say even if you're running SSB and CW, if you're running data modes, you probably use the wrong core in your 4-to-1 balun, and you can have problem. You can have thermal runaway. And we'll get into that too later. So most commercial 4-to-1 baluns are inadequate. Many are even worthless. And this is a part that I said I was going to explain the differences and show just why they're so bad. Now, this is the balun that's worthless. This is the single core. you've got two transmission lines. You have to have two transmission lines, but they're both wound on the same core. They have more turns, of course, but I drew these by hand. So this is a good one. Here they're so small, I didn't manage to wind the wire should be wound around like shown over here. But as you can see, each transmission line has its own dedicated core. This is a good balun, much better, 100% adequate for many antennas, but in most cases inadequate for the OCFD antenna, unless you add a choke. And the problem is, if you built the thing like most people recommend with number 43 ferrite, it's got a low Curie temperature. It's going to work okay in sideband, but if you're running digi modes, you're going to find out that your balun starts, the SWR starts creeping. It's called SWR creep. And eventually can even get thermal runaway and eventually even break. So this bad balun over here, now, like I said, the gurus of the industry, they explain why, and there's links on my website to read about them. The way this thing works, so in general, is you've got two 1-to-1 baluns like we see on the right, and here they're both on the same core, and we wire their inputs in parallel. If this is bifiller or twisted pair, it's about 100 ohms. So you get about 50 ohms on the left wired in parallel. We wire them in series on the output, and this gives us, a 4-to-1 step up. It gives us, 200 ohms on the output. So the first problem you see is if I wind, let's say I wind 10 turns over here on each of these, and I wind over here. First of all, you usually can't get that many turns on this because you've only got half of the space to do it. But the problem that you have when you've got inductors in parallel like this, inductors in parallel, and they're both equal, then you have half the inductance. So for the purpose of common mode impeding, you only get half the inductance, or the common mode impedance practically, out of this transformer balun that you would get out of the single core. So if I'm getting like 8,000 ohms, which is feasible out of a single core Guanella, I'm getting only 4,000. Now, in certain cases, that's enough. Other cases, it's not. And we'll look at that in detail later. This is another one where I missed it. So 1 core versus 2 core. Okay, now we're going to get into the to be or not to be. When I first heard about this was 12 years ago when I was looking into building my first OCFD. And a friend of mine pointed out that Tom Rauch, WHAI, explains and says that, that we should not use a single core. And I said, well, why not? Because every man and his dog is publishing designs for single core baluns, 4-to-1 baluns on the web. What's the reason? And so I sent an email off to Tom, and that was 12 years ago, and I haven't gotten an answer yet. I just asked him, well, how much difference does it make? Surely it can't be that much, or people wouldn't use it, and the balun vendors wouldn't build them. Well, the bottom line, it is that much, and the silly balun vendors are building them. So now let me show you what I did. Now I said, okay, if nobody's going to tell me, I'm going to find out. So I devised a test to test this. I sure wish I could make this thing go away. I can't. Now I made it worse. I can't get rid of my menu. It covers this. What you can probably see, hopefully I can't see, up here is a 40-meter OCFD connected to a physical half wave, not an electrical, and a physical half wave of coax. Why physical? Well, common mode current does not flow inside the balun, inside the coax. It flows outside. And the electrical quarter wavelength is, let's say, 0.66 times the physical. That's only inside the coax, not on the outside. So I was brainstorming with Steve. This was a dozen years ago, G3TXQ. And we said, what's the velocity factor on the outside? It has to be, like a big thick wire. So it's probably about 0.98. So roughly you need a physical half wavelength. You have the worst possible common mode current at the end of a physical half wavelength. And then I took the coax in order to generate common mode current. I bent it as far as I could, actually more radical than is shown here. The end of it was only about 5 meters away from the radiator. And then I built my 2-core balun, that's my 2B, and my single core balun, that's not a 2B. And I measured it with a scanning analyzer. The curve looked pretty good down here, except I had measured a 40-meter dipole earlier. I knew how that looked. I had measured the same OCFD with the coax in a straight line. I knew how that looked. And how they looked were at both ends, the curve was steeper. So this is actually flattened out as if somebody stepped on it. And it's common mode current causing it to flatten out. But it's not that bad. At least it looks like a dipole should look. Up here, I got a double dip. Now, if you only had an SWR bridge and you were measuring 3 or 4 places, you'd say, hey, great, this is a broadband antenna. Well, let's see how great it is. So that was step 1, just to look at it with an analyzer. Step 2, I applied 100 watts to each of these. Now, this is the exact same antenna. All I did was swap the balun. So same antenna, same place, just, swapping the baluns back and forth. So I applied 100 watts to it, and I took a clamp-on RF ammeter, and I clamped it on at the end. I mean, not just there, I clamped it on at several different places. I recorded all this. Worst case was at the end, and I measured how much current am I getting? Well, as it turns out, I was getting 340 milliamps of current on the single core balun, 105 milliamps of current on the dual core balun. So, first inclination, well, heck, that thing is 3 times as bad. Well, it's not as bad as I thought. Maybe that looks bad, but that's only 3 times as bad. Yeah, but wait a minute. How much power is there actually on the feed line? So this got back to, once again, brainstorming with Steve. Well, what's the impedance of the feed line? We said, well, it's thick wire, might be 600 ohms, maybe 500, maybe 400, but let's run with 500 and calculate the power formula, I squared R. So if you take that and square it times 500 ohms, we have 58 watts. From 100 watts generated, we had 58 watts in the coax. How about down here? We have 5.5 watts. So this is not 3 times worse, it's 10 times worse than this. Yet people are buying these all the time. Really good name balun manufacturers are selling these for lots of money. They're worthless. So this balun would be okay if we added a choke to it. So let's get back to Mark Twain. It ain't what you don't know that gets you into trouble. So you might not have known that you need a dual core balun, but you probably think you can get by with a single core because, after all, that's what everybody uses, isn't it? But that's what really gets you into serious problems. It's just a total waste of money to spend even 1 quid on one of these baluns. So the 80-meter OCFD choke balun. Yeah. Now I'm going to click this next thing and I won't even be able to read it. So what did it say? Something like, this is probably the most important slide on the whole presentation. I hope it says that. I can't see it. I'm going to show you 2 baluns. These are real live baluns, the pictures I actually made myself here. And I built both of these. I say this is a cold balun. This is a hot balun. Differential current is the current flowing inside the coax to and from the antenna. And if you have enough common mode impedance, you don't get common mode current. All of your current flows to and from the antenna inside. As long as it's flowing inside the coax, it pretty much does not heat the toroid. Over here, this balun happens to have insufficient CMI for an 80-meter OCFD antenna. Therefore, it has a lot of common mode current flowing on it. Show you what these are. These are real live baluns. The one on the left is the little one I showed you a moment ago, but it's using, this is basically number 43 ferrite. This is number 61 ferrite. Their permeability, 850 on the left, only 125 on the right. We're using thicker coax, but we're using less turns, 13 turns on the left, 18 turns on the right. And using the charts from G3TXQ, this says we've got about 8,000 ohms here and only 500 ohms here. Totally inadequate for an OCFD antenna. So what happens if you would try to use this? Of course, you have common mode current flowing not only on the coax here, but flowing on the coax around the toroid. It'll start to heat the toroid. Okay, and this is the biggest balun killer there is. Now, these two baluns, the one on the left is what I use in and Spiderbeam uses in the 807 HD antenna. And this is the Spiderbeam Yagi balun, and Nick showed us one. In fact, you can see one just above his head there. And the 5-band or 3-band Yagis, they've got multiple monoband Yagis. The radiators are center fed. That's where you have the least common mode current. The beams are usually high and in the clear, and this is the common mode impedance that you get on the various bands where you can use this, and that's enough for that application. It's definitely wrong for an 80-meter OCFD. It would also be wrong to call this a bad balun. It's an outstanding balun, a W1JR balun. Spiderbeam has been using this for 20 years, over 3,000 antennas in the field. So the only time I did tech support for 15 years for them. So the only time I ever had a bad balun, it had a hairline crack inside of it. And, we sent them a new balun for free, and that cleared the problem, So good balun, but it's the wrong balun. And that's what we have to watch out for, because the people selling these don't know what they're doing. There's one or two exceptions. And I don't want to start naming good or bad. I'm certainly not going to name the bad ones, at least not in public. And I'm afraid if I name the good ones, then I'll have some others say, why didn't you name me? So I'll just say there are good and bad. Do your own due diligence. Let's switch gears completely now. If anyone wants to take a stretch or so, we'll give about a 30-second to stretch or take a drink, which I'm going to do. I'm fighting off a cold, and I'm having to drink all the time to keep my voice going. So we're going to go away from baluns, and we're going to see, how do these things work? What enables them to work multiple bands with just a piece of wire? And it's not Harry Potter. The first thing we're going to do is look at a half wavelength on 80 meters, for instance. And we're going to see the distribution, how the current and the voltage compare along the wire. And as we know, current is maximum in the middle of the dipole, and we feed it there, and it's minimum at its ends, and voltage is vice versa. We also know if we feed it here at this point, we've got an impedance of about 50 to 70 ohms, something like that. It depends on the height above ground and the ground as well. Now, it makes no difference where we feed this antenna. We can feed it in the middle, in the end, or anywhere in between. Let's give it a place in between. Doesn't matter where we feed it. This relationship, voltage and current, it remains the same always. What changes, of course, is the impedance when we move along the axis here. So if we consider we've got about 50 to 70, say 60 ohms up here at the center, we could have 3,000, maybe 4,000 ohms, really high impedance down here. This place going to be maybe a couple hundred ohms if we feed it in here, right? So that's just general knowledge. So the question is, what happens if we bring in 40 meters? So let's bring in 40 meters. Okay. And by the way, voltage is not important. We're only going to look at current. So from the rest of the slides I show you now and how we make this work on the other bands, I'll only show current. I leave the voltage out. Before we look at 40 meters, so I want to reach an agreement, and this is where the speaker has the advantage. It's going to be a one-side agreement. You can challenge me in the questions afterwards, or at the send me an email. But I'll show you the gurus that confirm this. Anyway, we're going to look at SWR because, that's what everybody looks at. That's what our transceivers want. So many people think that SWR indicates the performance of their antenna. It has absolutely nothing at all to do with performance of an antenna. It's a mathematical ratio, basically. It's an indication of a match or a mismatch between two devices. And one of the devices is a transmission line. The other could be the antenna or the transmitter. But it's just a ratio. It describes a little bit about the ability of the transmission line to deliver power from the transmitter to the antenna. Tells us nothing about what the antenna does with the power once it gets it. And we're going to see on the next slide, basically just how little difference most of the time that will make. Now, I'm not talking about 50 to 1 SWR. If you've got 3 to 1, 4 to 1, 5 to 1. Here's an important thing here. Minimum SWR is not an indication of resonance. I mean, I was guilty of this too, and sometimes I still do because this is what I called it for 50 years. But it's actually minimum SWR is just that. It's SWR minimum. It's the frequency where you have minimum SWR, and it's not resonance. Now, it's not totally impossible, but maybe once in every 6 blue moons, you might find an antenna that has it. Most of the time, they're fairly close together, but resonance is a frequency at which inductive and capacitive reactance are equal and cancel each other out, and we refer to it as J0. I'm going to try to remember to say SWR minimum throughout the presentation. If I say resonance, probably mean SWR minimum. I usually catch myself, though, when I say it. So let's talk about loss due to SWR. Now, this is not total loss in your coax. This is a loss due to SWR. You all have heard for sure about Maxwell. I mean, he had the W2DU. No, excuse me, sorry. No, he didn't have the W. He had the Maxwell chokes. That is a W2DU chokes, which, if I can hold one up, here's one here. It was a coax. You really can't see it very good in the camera right now. I'll switch cameras later and you can see them closer. Okay, those were the chokes he came out with. But anyway, he wrote a book, and it's pretty much considered the Bible of transmission lines. And on page 1.8, he put this chart in here. It's the additional loss in dB due to SWR, and it's based on RG8, which at the time he wrote the book was pretty popular. And if we follow this up, and 100 feet of RG8, if we follow this up at 3:1 SWR, and we see where it crosses 4 megahertz and where it crosses 7 megahertz, we come across over here. It's less than 0.2 dB on 80, and it's about 1/4 of a dB on 40. That's a 3:1 SWR. Of course, it's a little bit more complicated than that because there are other types of coax. So on page 1.3 of the same book, he has this chart. You'll find this chart in every issue of the ARRL handbook. And basically what you do, you take your coax RG58, look up its loss for 100 dB, not 100 dB, 100 feet on the frequency you want to use it on. Let's say it's 2 dB, and you say you have an SWR of 3:1, so you go up the 2 dB line to get 3:1, and then you go across the left, and you say I've got 0.8 dB. And so that's how you can see the loss with it's the match loss plus it's a total loss, basically. It's the SWR loss plus the no, wait a minute, excuse me. This is the additional loss. Excuse me. So you would have 2 dB in the coax in general plus 0.8, so it's 2.8 dB. Sorry. Also interesting, in the every ARRL handbook, they've got a page where they talk about several myths about SWR. And one of them tells you, with a standing wave ratio of up to 6:1, with good coax, and in most reasonable links we use it, city links, nobody on the planet can hear the difference between that and a perfectly matched antenna. And if you follow this link on that page, you can read the entire thing. And as I say, I tell you how to look it up in any handbook. So people highly overrate the loss that they're going to get in SWR, and they think if they have 2:1 SWR, they're losing half their power in it. It's just not true. Okay, so now we'll continue with how we add bands. It's very simple. So this is 40 meters. If we look at the same wire, we transmit on 40 meters. It's now a full wavelength. So we have one complete cycle, a positive and a negative half cycle. 80 meters had maximum current here. 40 meters has 2 maximum currents. Each half cycle has a maximum at its peak. And the good news is, the magnitude, whether it's positive or negative, doesn't matter. The radiation intensity is equal. So to get a better view of what's going on, I'm going to look at the absolute value of all of these sine waves for this and all other bands. We'll just flip it upside down, the half wave. I blew it up a little bit bigger. So here you can see the 2 half cycles, and notice that they intersect at 2 points. 33.333% from one end, and then 66.666 from the other. But in the other way around, it's 33, etc. So one third the way in from either end, we have a point of intersection. Now, this was determined, in this in the 60s by K4ABT. He's silent key now, of course, but to my knowledge, he was the first person ever to feed an OCFD or to feed the old Wyndham with coax. And he built an ugly Ballon with 9 turns of RG11 on 8-inch, or it was 8 turns on a 9-inch core, but it just coax wound as an air core. But later he did a lot of measurements, and he said for an OCFD antenna fed at 1/3, if it's lower height, let's say 30 to 40 feet, so typical city heights, it's more like 230 ohms. As 90 to 100 feet, it's around 280, 285, something like that. And so I'd say, most of the time we're down in that area. But that's only for these feed points. If you move the feed point, it changes. Let's look at the next band. When I bring in 20 meters, we're going to find 4 half cycles. 2 of them cross at the exact same points. Well, when they're crossing at the same point, the current is equal, the impedance is equal. So if we feed it there, whatever the impedance is, it's going to be the same on all bands. And that's great, sounds great, but it doesn't have to be exactly the same. It needs to be close. Let's bring in 10 meters. I left 15 meters out. Bring in 10 meters. It's in green. It's difficult to see. However, notice it crosses at the exact same point again. Now, all of these curves, I drew these manually in PowerPoint. Later, I learned to do this, and I'll show you that with a software, a special program for this. But this was I did all of this 12 years ago. I've redone it since then, did it all in black and white back then. So this is pretty cool. Everything's crossing at the same point. We feed it here, feed it with a Ballon, and we've got 80, 40, 20, and 10 meters. Yeah. What happens when we bring in 15 meters? And as you recall, I said earlier, 15 doesn't work. And we're going to see why. It's going to be obvious why it doesn't work. When I bring in 15 meters, I'm going to leave off 10 meters. Just keep in mind it passes through the same points. The graph would be too busy if I showed it. So the dark black is 15 meters. So we have 6 peaks. If we look at our 2 points of intersection, the other bands all cross there. At that point, 15 meters crosses the 0 axis. And of course, the formula for resistance or impedance, Z is equal E over I. If you divide by 0, you get infinity. Not really infinity, but it can be really, really high. So you've got very, very high SWR there, and then you will real high SWR, like 20 to 130 to 1, you do get a lot of loss in your coax. Yeah, so this is the reason that 15 meters doesn't work. Now, one of the guys, the guy who sells these bad Ballons, and he's got a real reputable company, but we had a little bit of an argument recently, and he said the OCFD antenna was designed to work only on even harmonics. Total, utter nonsense. I mean, ridiculous. It has nothing to do with even or odd harmonics. Very simple mathematic. 3.5 megahertz for the 80 meters times 2 is 7, times 4 is 14, times 6 is 21. And 21 is a 6th harmonic, and that's an even harmonic. It's not an odd harmonic. So it has nothing at all to do with that. It has everything to do with just how the current is flowing at that point. And if you got current way down low, then you're going to have really high impedance and high SWR. All of this is still theory. It varies a little bit in practice, and that's why there's so much technology in this, because we go through all of these things so you can see exactly why the antenna behaves like it does. So far, we've only looked at the the classic bands. Let's take a look at the WARC bands. Before we do, I will remind you that till now we were looking at a point, 33%, where all the impedances were going to be equal. Well, at this point, I'm going to say, let's change our goal. Our antennas don't have to have 1-to-1 SWR. I mean, most transceivers, a lot of transceivers, good transceivers, will work with 3-to-1 SWR even without a matchbox, but most of them nowadays have a matchbox, and 3-to-1 certainly isn't enough to be detrimental to the signal. You might have to turn on your tuner. So if we accept 3-to-1, this would give us a range compared to 50 ohms between 17 ohms and 150 ohms. But we're going through a 4-to-1 Ballon, which means, 4 times 17 and 4 times 150. So we've got a range between 68 ohms and 600 ohms. Now, see if you can see that, that's a really broad range that we can be in. And if we can get our curve passing anywhere through that range, it's going to be less than 3-to-1. It's going to be a usable antenna. So what I did was I started looking for a place along here where all of the curves were somewhere up close to being the same. Didn't have to be exactly the same. I identified two ranges. One of them was at 20%, and the other one was at about 30. It was 29.5 or so. I did all of this in PowerPoint. I didn't use a computer program. Later, I used computer programs, but at the time, I was in a hurry. I wanted to get an antenna up for CQ Worldwide DX. So I identified these 2 points. Which one do you use? Well, the bottom line, if you're a contester, it makes no difference. They both work. What changes, though, are the arc bands. So if we look at how 30 meters flows, 30 meters is nice and high at point C, 20%, but it's not quite zero. It's a little bit, but it's very low at point D. So if you want to work 30 meters and the other bands, the other classic bands, you are going to be looking to the 20%. Unfortunately, this 20% has 30 meters, but it does not have 17 meters. 17 meters, and this just got too difficult to do in PowerPoint, but I'll show you how you can see this in just a second. So we've got these 2 points, C and D. D has 17 meters, but no 30 meters, and vice versa. So you can't always get what you want. I guess most of you recall who sang that, and it's a compromise. The good news is, though, if you take either one of these antennas and take the band that supposedly doesn't work and you use an antenna tuner with it, you can still work a lot of DX with it. It does work. And it's you're going to find out in a minute, it's not actually as bad as it is. There's some other things skewing the curve, and we're going to learn exactly what it is. So the current is actually a bit higher here than it's showing here. But it is a compromise. So 23 years ago, there was a German ham, DL1 VU, and he wrote a book. In German, it's called Windom und Stromsummenantenne, which translated means Windom and current sum antenna. Where's my camera? And let's see if I can find me. I've got a problem. Abracadabra, how to make the book appear. Well, bear with me 1 second. So change cameras. That must be my background. So this was his little book. That's not going to work. Excuse me. Anyway, in that book, it was all about Windom, the old single wire Windom, but then about the coax fed Windoms, and you could learn all about the history of the Windoms and so forth. We'll go back on the other camera. But he also had a nice program in there for predicting where to feed it. Trouble was, it was in DOS. And, you know, typing in manually 100 lines of code in DOS, I figured I would never manage without mistakes. I just didn't bother. So I just, I used my own method here, and I got some results that work. Luckily, 10 years later, another guy, Klaus DG0KW, he rewrote the software. He ported it to Windows and made a download available. It's free for anyone that wants to use it privately. So I've got a link here. If you go to my web page here, you can download the software. You can download the user manual. That's the good news. The bad news is it's all in German. And then if I can get, there we go. The good news is, though, I have translated the user manual from German to English. And that's posted on my website. You can download it there. It's pretty easy to use the software once you understand what you have to do. Oh, Nick, I think we've got that echo again. Hello, Nick. Oh, I don't hear you, Nick. Turn on your mic.
No, that's okay. No echo. It was someone's audio popped up.
Oh, okay. Great. So I've written the manual into English, or translated to English, and then you enter the data, like what bands you want and so forth, and what's the thickness of your wire and etc. You enter that into a template. The slots are all labeled in German, and I've translated it into English. So if you print out my template with the English translations, it's very easy to see, what you have to enter in each of the slots. And after you've done it 2 or 3 times, you won't even need to look at it anymore. You know exactly what to do. So, and you can download all of this on my website. Follow the link here. That link takes you to, as I said, information page for slide 28. But this link here, and there you'll find a repeat of this link. So either one will get you straight to that modeling software. Of course, there's other software, EasyNet, which most people work with. A few months after I built my antenna, a friend of mine modeled it. It's DJ18T. And he came up with this. First glance, that looks outstanding. 80, 40, 20, 30, 20, 15, 12, 10. I mean, what more do you want? Actually, it's not quite as good as it looks, because what you don't see is the exact frequency. And it turns out 30-meter band is slightly to the left here. Okay, so this was measured on my antenna, the first one I built. I mean, the first year I measured it with my MFJ 259B. So I took about 100 data points and I drew the charts manually. It was ugly. The second year I splurged and I bought a scanning analyzer, a Rig Expert AA54, and that made things a lot simpler. You could really see the curves. Here you can kind of see 80 meters was a bit low in the band, and 30 meters, the peak is above the band. 20 meters wasn't bad, 15 wasn't bad, 12 peaked below it, but it's still quite low. All of these are below 2-to-1. And I ran CQ Worldwide DX contest, barefoot with the transceiver with no tuner, or with my amplifier with no tuner, no problem. Switch bands, no problem. Problem was 17 meters. 30, you might have needed an antenna tuner, but it's not a contest band. So how do we know where to feed the antenna? Well, as I said, there's antenna modeling software, and in my opinion, there's no need to model the software. I've never modeled with NEC. I use that other software, but I see no need to model it because every man and his dog has already done it. And John Young, gosh, 15 years ago, or well, maybe 12 years ago, a long time ago, he modeled it, made models for 160 meters, 80 meters, 40 meters at a couple of different heights. Basically, he modeled till the cows came home. He came up with an Excel spreadsheet, published all of his data into a spreadsheet. There's about 6,000 data points in here. As he modeled it for each band, we've about 8 bands or something like that. And then he modeled it for 50 ohm feed point, 100 ohms, 150, 200, and 300 ohms. And, you take that many different, and then he modeled it in half percentage increments, at the end at 0, 0.5, 1, 1.5, not exactly, even numbers, but every half percentage, he had another model. So we come up with about 6,000, and you can see absolutely nothing on that. But having been in marketing and, business management, I learned to work with Excel, and it's got a nice feature called hide. It took me about 10 or 12 hours to go through it. Everything was 50 ohms, 100 ohms, 150 ohms. I hid. I only looked at 200 and 300 ohms. And then I went through, on one of the charts, he shows like every 100 kilohertz in the band. So, I blocked most of that out too. And I just looked at it briefly and I said, wait, there's no point in looking at 300 ohms. It's not better anywhere. So I got rid of all the 300 ohms, and I finally came up with a nice little chart like the one on the right. Nice overview, had all of, my short list of what I might want to use for 80 meters. And here it's very clear to see exactly where you want to go after you blow it up. And so when you blow it up, you can start looking at how it is across the bands. And basically the contest bands interest me, but I didn't want to have it too far off on the WARC bands. As I said earlier, there's 2 points. This is down around where I had point C, and this is up around where I had point D. As I said, okay, let's focus, let's hone in on these 2 places. So I brought those in, and I just put in some of the bands here because I want to show you probably the most important thing to learn about tuning the OCFD antenna. And that is, we look at 20 meters and 15 meters. We're going to see why we tune OCFD antennas by observing these 2 bands, not by looking at 80 or 40. We look at these 2 bands. Okay. And what you see is if we move the feed point closer to the end, 20 meters gets better, 15 meters gets worse. Okay, 12 meters gets better too. We go the other direction, vice versa, 15 better, and these two get worse. Now, if we move up to the other range, it's still the same scenario, but it's opposite. Closer to the lower number, 20 and 12 get worse, 15 gets better, and vice versa. So which feed point is best? And there's no right answer. It all depends on what you want, you know? And if you're an SSB operator only or a CW operator only, you might want to be 0.12 or 3% different from these. And, you know, like I said, he only did about every half percentage point. So I actually ended up through my field work at 29.7. So that's where I put mine. But you basically pick something here, you build the antenna, and like always, you leave the ends a little bit longer, you fold the wire back, and you go to the field, and you start measuring. Now, once again, here's the link to all of these, to these tables, to the original tables, to the files. You can download the Excel files at that link. If any of you are in any of the antenna groups, and I know some of you are, I recognize your call sign. You've probably seen this dozens of times. This is what, for some reason, all of the guys like to do. They build an antenna and they show this lousy graph because you can't see any detail, you know. First of all, this first one I took with a, okay, this was with my new analyzer. The first time I did it, the analyzer only measured 100 data points. So if you scan 30 megahertz, your data points, your measurements are far off, and it just interpolates in between. So it's going to be off quite a lot. This one was fairly accurate because it measured every 60 kilohertz. But the problem is you can't really see much on the bands on these little things here. So that's why I say this graph is worthless. Other than it, I always do it. I always measure this. It's just a quick look to see is the antenna working or not. Because a couple of times I did the scan and the graph was up here at 10-1 and it went a straight line all the way across. And I had a bad solder connection and a coax connector, you know. So it's a quick sanity check, but it tells you basically nothing. So if you want to know how your antenna is working, you have to really look at each band one at a time. So I use 250 data points here, which gives me a measurement every 4 kilohertz. The 807 HD is my, well, I say my design. Spiderbeam sells it. They sell different versions of it. This happens to be the US version. So it's, you know, the minimum SWR, I almost said resonance. Minimum SWR is up around 3,800. We have another one for general hams and technician hams. It's resonant up around 3,900. So the next, not resonant, minimum SWR. So the dip is moving up here. We also have, we can put the dip in the digi band or the CW band, you know, well, actually the same, down around 35, down around here, have the minimum SWR. 40 meters is the same, or the other bands are the same. What we do to move this does not affect the other bands. And we'll see how to do this towards the end of this presentation. And we'll learn how to build it yourself in the next presentation. So here you can see in 40 meters across the whole band, even up into the US band, below 2.2 to 1. If we look at 20 and 15 meters, we're below. This one goes a little bit higher here. You could, let me come back to that. When I went to 10 meters, I had to increase the scan to 3 megahertz because, you know, it's a wider band. What I want to focus on is 15 and 20 meters. Here you see 20 meters, its worst SWR is on the high end of the band. And on 15, the worst is on the low end of the band. So if we were to make the antenna longer, then that would bring 15 meters in a little bit better, but it would make 20 meters even worse. And if we made it shorter, vice versa. That's why I say we have to tune our prune our antenna by watching these two bands. And it's every case, regardless of where I put the feed point, it was always this case. And by the way, if you're moving the feed point inch by inch, you also find these two move in opposite directions. So forget about wondering where to set your antenna on 80 meters. You set it somewhere low below the band. I'll show you, you know, where I recommend setting it, leaving extra wire, but you tune by watching these two bands. Now we're going to come to a fun part, and I'm going to debunk the myth that the OCFD is a harmonic antenna, because it's not, but it almost is. Let's say you work SSB on 80 meters. So here in Europe, we want to put it at 3,700. Well, the second harmonic is 7.4, 14.8, 22. All of these are outside the band. And for the States, we put it at 3,800. We're way outside the band. If we put our SWR minimum for CW and Digi down around 3,550, we get it inside the band. So, you can't make your antenna resonant, minimum SWR inside the 80 meter band and expect to have low SWR inside the higher harmonic bands. It's just not going to work. And by the way, this is only half the story. It gets worse. Now, this is the fun part. So let's say if you look at my picture on your screen, and me, you'll see I'm out here in outer space, and I've flown out here so I could examine this antenna. This is an 80 meter dipole in outer space, in free space. It's exactly half wavelength long, 2/4 wavelength. So we have 1/2 wavelength end to end. And knowing how that worked really doesn't help us much, because I don't know anybody that builds antennas in outer space. I know a couple of guys that want to try it. They're looking to move to outer space. So one of them is Elon Musk. The other is Richard Branson. But until they get out there, there's no sense in looking at that. So I'd like to have Scotty beam me back down here on Earth where you guys are at. And let's take a look now. Let me clear this out. At how our antennas work here on Earth. Here on Earth, we find we have two things that affect the length that we need to cut our dipole to. The first one, velocity factor, is pretty clear. Wire has typically a velocity factor about 0.98. So we shorten the wire by 2% so that, because of the velocity factor. So it only needs to be 98% as long as a physical wavelength. Obviously, these are exaggerated so you can see the difference. It's absolutely not to scale. But the second thing is end effect. When we have a wire on an antenna, unterminated over ground, we have something called end effect. Now, this will generally cause us to have to shorten the antenna by 4 or 5%. Okay, so we end up with having the antenna the wire really only being 93% of a 1/4 wavelength in each half. That's on 80 meters, but we want to work 40, 20, 15, and 10. Let's see what happens on 40. On 40 meters, we'll find we have 4 1/4 wavelengths. The outer 1/4 wavelengths, they're shortened by end effect and by velocity factor, but the inner 1/4 wavelengths, they have no end effect. They only have the velocity factor, so they need to be 98%. So we're too short. The antenna is too short. The antenna needs to be lengthened longer than it is. Here's how long it is. It needs to be this long if we want it to work on 40 meters. But if we cut it this long, then it's resonant. Minimum SWR on 80 meters is going to be below the band. The next thing I'd like to do is look at all of the bands. Well, not all of them. I left out the walk bands, but let's look at these harmonic bands. It's a little bit complicated. We'll go through it step by step. Red is what we have if we just built an 80 meter resonant dipole. If we look at it at 40 meters, this is the same thing we looked at on the previous page. We've got the 2 inner 1/4 wavelengths too short. On 20 meters, we've got 8 1/4 wavelengths, and 6 of them are too short. Down here in blue, this is what we need. And we looked at this. This is the same as on the previous page. It needs to be a little bit longer. But on 20 meters with 6 of them too short, it has to be even longer. And on 15 meters, we've got, I don't know how many of them, 8 of them probably, or whatever. Anyway, the higher we go, the farther apart these go. Now, I'm going to show you real live antennas and measurements I've done that will, show you that this is actually what's happening. But this is why it's happening. So we've not only got the fact that if we tune somewhere down in the low end, but inside the band on 80, we're outside the band. We also have got this end effect problem that makes us even worse outside the band, which tells me we have to make the antenna on 80 meters even longer. As you see, it's not a harmonic band. Now, this is real life. This is no longer just theory. The first thing I've done is I've just put in straight factors for harmonics: 3.5, 7, 14, 21, 28. So, it's 200%, 400%, 600%, 800%. Now let's look at real live antennas. I've got two. It's actually the same antenna. All I did was move the feed, the balun, same balun, same antenna. I moved the feed point. 33.3% is the classic OCFD antenna. 29.7 is my favorite. For some reason, I had a shift of 10 kilohertz for the frequency of minimum SWR. Not going to worry about that. If I measure the same antenna on 2 different days, there can be 5 kilohertz anyway. So that really isn't a problem. Here's what I saw. When I go to the second harmonic, this one was 202% of that number. This was 204. This is 410, 407, 612, 615, 824, 827. So this percentage continues to get larger and larger. So the minimum SWR keeps wandering higher and higher in the band. That's why we really have to cut the 80 meters pretty far below the band in order for it to work on the higher bands. You wonder, this is like a never-ending story, huh? But it gets even worse. There's one more, but one last thing that we have to be aware of and beware of. And we've already looked at this earlier, but I'm going to show you how much difference it can really make. Common mode current causes SWR to skew higher up the band. And the question might be, how much? First thing I did was build an 80-meter dipole. I put a 1-to-1 current balun, choke balun in the center of it. I calculated with the dipole formula to be 3480, measured it, came out to be 3450. I wanted it below the band, and I didn't know how far to go, but I thought 3480 might be enough, and I put it to 3480, and it turned out to be 3450. I learned later with this antenna why that is. When I built this antenna, it was the first time I used the really thin wire. It was AWG, American Wire Gauge 26, very thin wire, about a 0.5 millimeter diameter. I'd always built with number 18 in the past, which is what Spider-Beam uses in their Yagis. Guess why I built with that wire? Got it for free. So as it turns out, the thinner wire, it's got a lower velocity factor than a thicker wire. So much so that if I cut the antennas to be minimum SWR on the same frequency, the thick wire was 40 centimeters longer. What's that in inches? 2.5, 20 inches or something. No, not that, whatever it is in inches. But anyway, it's quite long, 40 centimeters longer for thick wire than for thin wire. And that's why I came out so low here. I just left it because I really wasn't interested in building a dipole to use. I was interested in finding out how the baluns compare to each other. So keep this figure in mind. This is the target we're going to be looking for. We need to be near that at least. Here, 29.7% split. G3TXQ, of course, silent key now. At the time I did this, he was not. He's got this web page, one of many web pages, where he actually shows a lot of different one-to-one chokes and tells how much common mode impedance they have. And I'll use his charts to define these. This is a balun, relative expensive, outstanding quality, but no good for an OCFD antenna. It would work in a loop, but not in these antennas. It's because he used number 52 toroid, relative low, 250 permeability, and he only used 11 turns. And it's a 4-to-1 guanella. So you have paralleled coils. So you end up with only 500 ohms, and 500 ohms is nothing. And look where minimum SWR landed, over 400 kilohertz, higher than it should be. I said, okay, not to worry, we'll build our own. So I made one myself, and I used number 43. It has 800 permeability, and I managed to get 17 turns onto the cores, to the 2 cores, which gives me 4,000 ohms. 3515. Well, I'm not where I need to be, but it's certainly a lot closer. I want to come back to this in a second, show you what happened when I added a choke. So then I had discussed this with Steve, G3TXQ, and learned that I just couldn't get enough common mode impedance with a dual core 4-to-1. Had to go to a 1-to-1. One of the things I had done, I tried using a 1-to-1. This is the FT240-43, a 1-to-1 choke balun. I first put in a dual core here, worked, but I thought, heck, I don't need the dual core. I don't need any common mode impedance. So I switched to a 1-to-1 Rutherford, a voltage balun, excuse me, not 1-to-1, 4-to-1 Rutherford balun. So it's a combination of two baluns. I call it a hybrid balun. It's called that in ham circles, but the commercial engineers, they like to call it a compound balun. It's not a new idea, but it wasn't very well known in the ham circles. So I built this. It has about 8,000 ohms. The first one, which was using the two of these FT240 cores, it came out to 3440. There's even 10 kilohertz below here. Of course, part of the difference might have been the weather of the day I measured or something, but basically that's ballpark, okay? I repeated the same thing with smaller cores, with the FT140s and with the FT114s, keeping the same number of turns count. This isn't really 8 kilo ohms. It reduces a little bit, and Steve didn't measure these, so I have no idea, and I didn't bother to measure them. I was interested in the results because the results kept coming in at 3450. So, you know, my tiny little baluns were blowing the socks off of this expensive thing up here. You know, these probably cost me 20 pounds to build or something like that, as opposed to about 100 pounds to buy the one up there. And the difference is mine work and that one does not. Okay, so this is what is confusing about all of this, and especially in the States, there's a lot of balun vendors, OCFD antenna vendors, and they're building their OCFDs and using this balun on the top or one like it. Their 80 meters SWR is resonant inside the band, and it looks great, you know. But if you're resonant inside the band, and you're also resonant on your, 40, 20, 15, 10 meters inside the bands, you've got an awful lot of common mode current on your coax, and you don't want that. So you must put, not resonance, minimum SWR below the band. I went back up to each of these antennas, and I took, let me get it again, and I'm going to switch to the, if I do this, you'll see it a lot better. There's somewhere around here, none. Here you can see it a lot better. This is basically a Maxwell choke balun. So I just added this Maxwell choke. And while I'm here, I can show you some of these others. This is the FT240 core. That's a 1-to-1 Guanella. It's actually the same one, identical one that I used in the big balun of my hybrid. This is my little one, my tiny little one. Let me put it up and compare them. This is what we use in the 807. And like I say, I've got a lot of customers that run a kilowatt SSB through this thing. Never had anybody burn one up. I did have twice complaints in FT8. The balun will get warm and you start to get SWR creep already at 200 watts. So I worked with one of my customers in the States and a good friend of mine over there. And I had him rebuild the top one. I had him take this apart and stack two of these cores together and rewind it. And when he did that, he was able to get 600 watts through it before he got SWR creep. So as you can see, it really doesn't have anything to do with the size of the balun. It has a little bit to do with the size of the balun, but it has a lot more to do with the design of the balun, what material you use, basically know-how. And apparently most of the people building these antennas don't have the right know-how. So let me just, I think I can click that out and get back into my comfort zone. Where am I over here? Okay, so as I say, I put this one Maxwell choke on my dual core 4-to-1. This dropped to 3480. It's about 30 kilohertz above where it should actually be. Should be at 3450. So I said, hey, that's close enough for government work. There's a little bit residual common mode current on it, not enough to worry about. I'm sure it would be good to go with that. But on the other hand, I see no reason to use the dual core. I can tell you, I will tell you more about this in the next presentation because it's shorter than this presentation. So I then went up and I put the choke on this one, on this poor balun, and it dropped from 3890 down to around 3700 or something like that. I then put a second one on it. It dropped around to 3550, or I don't remember exactly where, but I kept adding these chokes. It kept getting better. So then, but I only had two. So then I took this choke. I hope you can see it, but you saw this earlier. It always goes backwards, doesn't it? That was the little one, the 1-to-1. And I put that onto it, and then it dropped to 3450. So it's very obvious. The cause here is insufficient common mode impedance. And that's what's wrong with about 90% of the OCFDs that were ever built in the history of the antenna. And I don't know why it took so long for people to discover that. Maybe because I put 5 years into finding out. Okay, so a warning for people that have built their own or bought one. If you have bought or built an 80-meter OCFD antenna with SWR minimum inside the harmonic bands, which is good, but it's also inside the 80-meter band, you've got a lot of common mode current, significant common mode current on your feed line, and that's bad. So, and if you do have your resonance or your SWR minimum too low, very simple solution. How to fix it, I'm going to show you in the next slide. We're going to build one in the next presentation. It's through a capacitor. And if you got common mode current issues, well, the problems of balance. So use a good quality 4-to-1 balun for the impedance transformation, and use a choke that OCFD. Okay, so this is how we fix it. Here's our OCFD, not to scale, just any OCFD. We're going to cut it the overall length right in half, put an insulator in it. We're going to insert a capacitor across the insulator to connect the two wires back. We have to put a bleeder resistor across it. Otherwise, static electricity in a decent thunderstorm will kill the capacitor. The first ones I built look like this. I just took a tiny little piece that was about, I don't know, 1/2 inch by 2 inches, drilled 3 holes, weaved the wires in and out, and then soldered resistors and capacitors. I say capacitors and a resistor. I had one single 3-watt resistor, but I had several capacitors. Show you why you need several capacitors and not just one. I mean, you could use a big doorknob, but how do you know what value you need? And the advantage of combining lots of little capacitors is you can kind of prune the frequency where you want it. So the capacitor raises the resonant frequency as well as SWR minimum on the 80-meter band with no significant change to the higher bands. The value of the capacitor determines the desired resonant frequency. So by varying the capacitance, you can change where resonant frequency again, huh? It does change resonant frequency, but we're more interested in SWR minimum. And Spiderbeam, like I said, they sell these with 4 different versions. All they're doing is putting this piece, they're changing it in and out. They're actually swappable in the antenna. And so what I do is for contest, I'll put in the CW cap board, and for SSB, I put in the SSB cap board, and then I don't have to use a tuner. So larger capacitance, and this actually went opposite as I was thinking, but I guess I didn't know what I was doing. A larger capacitance lowers the frequency, a smaller capacitance raises the frequency. And in part 2, I'll give you ballpark numbers to start with and show you how you can tune it. Is the next thing that kind of bugs people. We're used to, if we have a fan dipole, we tune every band independently, but OCFDs don't work like that. If you make it longer or shorter, it changes all bands at once. So, it's an interacting between bands. You can't adjust individual bands without affecting the others. When you make length adjustments, higher bands are affected much more so than lower bands. If we trim it a bit, make it higher, 10 kilohertz on 80, it's 20 kilohertz on 40, 40 kilohertz on 20, 60 kilohertz on 15, and 80 kilohertz on 10. We only move 10 kilohertz down here. So, you do have to take care of what you're doing. And always check the SWR on all bands after making adjustments. The OCFD is a great multi-band antenna as long as you are willing to compromise a little on SWR. Better to optimize on the high bands because, on the low bands, the SWR, the loss in the coax isn't as high on low bands. So, I always pay attention to the high bands. Now, what works good does not mean, what works does not mean it works good. In the antenna groups that we're in, we've always got people logging in and telling us how great their antenna work, and they listed 3 QSOs that they had. Well, Tom Schiller, N6BT, he was the founder of Force 12 Antennas. He published a really funny, interesting document or article in QST long ago. I've got links to it though. Everything works. And what he did, he took a light bulb. He took a 150 watt incandescent Thomas Edison light bulb, and he mounted it on a wooden fence post 6 feet high, and he put immediately an RF choke attached to it, and then ran coax. And then he ran I don't remember which contest he ran, but he ran one of the DX contests, 100 watts. And on a single weekend, he worked all 7 continents on a light bulb, 6 meters off the ground. So everything works. So, when somebody tells me they work something, so what? I mean, if I win a contest, and that's meaningful. Now, this is my favorite slide. That was my favorite car because that was my first car. Got it in 1964 when I got my driver's license. If you notice from the picture, I was a bit thicker back then. I've lost weight. The interesting thing, why I'm showing this, 1 year before that, I built my first Wyndham. And a few years later, I built a real OCFD antenna, but I was building them kind of like these Morse minors were built. Now, I was living in Oklahoma. As far as I know, I had the only Morse minor in Oklahoma. But for me, that was the best car in the world. Today, you can see car technology has advanced. This is the car I have today in my dreams. I've never even seen one on the road. But, some OCFD antennas are more efficient than others and free of common mode current if you build them right. And the difference between these lousy antennas back then and, to the good antennas today may not be as dramatic as what we see between these two cars, but boy, it's huge. And it's a big advantage if you build it right. So this brings us to the finally working good and working bad, or what works good. For me, working good means this. I want all of my radiation coming out of the radiator. That's desired radiation. I'm going to chase DX and work all states and work contests and all zones and all that. Here's what I don't want. I don't want to chase these two. I don't know if any of you guys have earned these awards yet. This is worked all smoke detectors, and this is worked all televisions. So this is undesired radiation, and the last thing we want is radiation from our coax, even though there's people that claim it's good. That might have been good 60 years ago, but with wall-to-wall consumer devices in our houses, we do not want this. Summary, probably the last slide. The OCFD antenna can be a wonderful, efficient multiband antenna if you build it right. There's no such thing as a best feed point. You're always hearing people claiming they've got the best. There's no such thing. It's horses for courses. The balun is the key to success. If you get your balun right, you're halfway home. A single core 4-to-1 balun just simply does not work, and do not use it. And a dual core 4-to-1 balun is probably not the best idea. There's another reason. I'll explain that next time. There's another reason it's not a good idea to use these. Hybrid baluns or compound baluns, that's the way to go, but you have to build it yourself because there are a couple being sold on the commercial market. I know of 2 companies selling them. They both will work sometimes, and one of them will fail quite a lot, and the other one fails under certain circumstances. The second one's pretty good all the time, except in digi modes. So I went through 2. The OCFD must have SWR well below the fundamental band. Tune trim the length to optimize SWR across 15 and 20 meters. Raise SWR minimum in the fundamental band with capacitor. Beware of vendors selling snake oils because there are plenty of them out there, especially on eBay. To be sure, I recommend you do it yourself, and we're going to learn how to do that in part 2 of my presentation. So this basically concludes it. I'd like to just point out down here, Once again, here's the link in your PDF. This should take you straight to the page. Otherwise, go to dj0ip.com and look for HH2G presentation, and you'll find it in there. I've got several email addresses, and the one some of you may know me under, Rick at dj0ip. Do not use it, because I get 50 to 100 emails there every day. Sometimes emails get lost or they stay in there for a week. Please send questions to this. Hitchhiker's Guide to OCFD, so -OCFD at area51.com. And they'll be only questions about this antenna. And the 3 websites I have, I didn't want 3, I wanted 2. I wanted this one and this one. Ran out of space on this one, so I had to buy another one. So I've ended up having 3. So my information can't be found on a single web page. It's spread across 3. So I'd like to open it up for questions. And Nick, I'd say before we do, let's take a 2 or 3 minute break. Everybody can, go to the bathroom or get a coffee or whatever, get a stretch, and then we'll open it up for questions. Nick, is that all right?
Absolutely brilliant, Rick. Yeah, thank you very much. Right, should we take just a couple of minute break to either go to the loo or go and grab a drink and then come back for any questions to Rick? Yeah, thank you, Rick. Well, just a couple of points. If people haven't spotted, I put into the chat the 2 documents that Rick was talking about. One was the handout with all the links on all the web pages. That's the first one. And the second document I put in was the article that appeared in Radcom in December 2017 by M0RZF Rob, who I've been in contact with. And incidentally, for those people up here in Yorkshire, that antenna in Radcom was used by G3UNA at the Knaresborough Amateur Radio Club as a club project to build a version of it. And G3UNA is also written on that subject as well. But they're the 2 bits that I've copied into the chat, and you can download the documents directly from the chat and have a look at them in your own time.
I'm back.
Okay, Rick, and okay, everybody else. That was some presentation, Rick. I have to say, there was, as you know, and you and I know, because we've been talking about this for some time now, an awful lot of information in that first part of the presentation. And this is really the taster to the second part of the presentation, which is coming up next month, which is more going to be about putting this into practice. So the practical side of building the antenna and building the balun. And they're the 2 things that Rick's going to talk about in a lot more information and detail in part 2. So has anyone got any questions to Rick from tonight's presentation? Or has this just been too much for everybody? Anyone got any questions? Very quiet.
Looks like I got everybody put to sleep. But I told you before, the questions will come once we learn how to build the thing, because I think that there you can get into quite a lot of questions. But this was the theory.
We've got one here, Rick, M0KIL. Do you want to go ahead?
Yeah, thanks. Excellent talk. It's reinforced one to my prejudices, but I have a question basically regarding the placement of the ferrite. Because of the weight of the ferrite, obviously the area is going to sag quite a bit. And with the easy availability of 300 ohm ladder line, is there an option to have a 300 ohm version with the ferrite on the ground?
Let's see. Okay, yeah, my mic's on. Yeah, there is, and it's a lousy solution.
Okay, fine.
No, let me explain. Let me explain. First of all, I don't know why it has to be heavy, because how much power do you run? As far as I know, you're allowed 400 watts. Or how much power? Well, no, you may not want to say how much power you're running. Let me hold this up again. This thing weighs nothing. I can pull out a scale and weigh it, but you don't even have to put them in a box. Quite a lot of the antennas I build, including some of them I built for Immel for the Rocco expedition. I didn't put an enclosure in them. I just built them like this. What I sometimes do, once they're all soldered and all that, I coat it with the liquid electrical tape. Just paint it a few thick coats, and that's it. It's just fine. To the contrary, they actually cool better. So like K9AY in his RF choke cookbook, he recommends not using a balun enclosure. Just leave it out open because it will cool much better. So, but you can build it lighter. Here's what happens when you use 300 ohm. Now, I'm not against using 300 ohm, but I'm against using it in an OCFD antenna. If I want to use it lightweight and 300 ohm, and then if you use 300 ohm, you're going to have to use a balun, and I'll tell you why in a second. Not a balun. You're going to have to use a matchbox, and I'll tell you why in a second. So the problem with this is you have so much common mode current at the feed point of an off-center fed dipole that you absolutely need a balun you need a good choke balun at the feed point to block the common mode current. If you don't have that, you're going to have common mode current all the way down your feed line. And you can put a balun down there, but here's what we've experienced in doing that. When you cut the antenna, as I'm going to show you how to cut it, similar lengths and all that, and should work, and you put a balun in, it does work, and then you put 300 ohm, and then you drop down to a balun somewhere else. This changes the antenna, because the feed line actually becomes part of the antenna. And so it's all out of resonance, and you most likely will lose a band, maybe two bands, and it's okay in the field to have antennas with common mode current on the coax, but you certainly don't want to have that around a housing area. I showed you one of the presentations here earlier, one of the slides. I actually saw as much as 58 watts on the coax with just 100 watts driving into it. If you're running high power, you can have an awful lot of radiation out of your feed line. So, I would recommend not doing it, but it does work. If you can get it to resonate, and you can always do that with a matchbox, you're going to work station with it just fine. But for reasons of common mode current, I don't recommend doing that. If you decide you want a lightweight antenna, move that to the center of the antenna and run it down and match it with a matchbox. That's what I ran for 50 years. Works just fine. So, and some people swear by it. Some people have done it and they say, hey, they're getting by with it, but other people have. I tried it once too. And, I had too much common mode current. I said, forget it. And that's why I designed lightweight baluns. The problem is, try to buy a lightweight balun. It's next to impossible. Everybody's selling baluns that saying they're 5 kilowatts or something. They weigh 3 pounds. So do you not have the possibility to place your balun on a pole or something, or hang it on a tree, or?
Oh, sure. Yeah. It's just I'm thinking in theoretical terms. But, at other times I've used a telescopic pole to, a fiberglass pole to support the feed point.
Yeah. Okay. Well, that's my answer. You can try it, but don't be surprised if you lose a band or if you have trouble with common mode current.
Sure. Okay.
I'll just make another statement. A lot of guys, we've got this OCFD group, which I could highly recommend joining. I'll put a link onto the other pages here, the web page there. It's on Groups.io, and we've got, I don't know, 1,300 members or something like that. A lot of guys have tried that, and all the time you have people, new guys come in, and they've built this thing, and their OCFD doesn't work. One band or another is just not working, and they describe it. And for the reasons you just named, they just came out of coax, just straight out of coax, and dropped down 10 or 20 feet, and they put their balun there. And I said, move your balun to the feed point. And so every time I said that, every time they moved the balun to the feed point, and it worked like it should. You just don't want to have your balun away. You want to choke the common mode current before it hits the feed line.
Yeah, fine.
Lovely, thank you, Keith. And that's a good tip from Rick that I know he'll talk about again on the second part of the presentation. But the point he makes about actually there is no need to stick the whole balun into a box. It's the box that increases the weight of these things, really does. And then particularly if you fill the box as well,
Yeah,
top of the balun.
well, I will show. Except I call it an open frame. I didn't know what else to call it, so I call it an open frame balun, and I'll show examples of what I've used. There's one company in Germany selling back planes. It's called DX Wire for open frame, but I've designed one that you can build out of. I used plexiglass at first, but I didn't like working with it because when you drill holes or something, it would melt and all the gooey stuff would stick to the drill bit and all that. So I switched to FR4, which is epoxy board, like they build printed circuit boards with, but you can buy that without copper and at various thicknesses. And this is outstanding then for back planes for a balun. And so I typically use that when I build antennas. And, I've probably built, well, I definitely have built over 100 baluns. Probably 150, something like that. Just crazy. Well, Emil's so crazy about climbing and stuff like that. Well, I'm crazy about balance.
Yeah, and it may be. I mean, in that second article by Rob that was published in Radcom, and I know you've done some work on that as well, Emil. Is the concept of an end-fed off-center fed dipole as well, which is an interesting one that would solve the issue that Keith was raising anyway.
Yeah, depends on how he's going to string it. I don't know if he wants to string it as a flat top, but it would definitely do that, or an inverted V or how. What I want to say about Rob, he and we worked together before he published the article. I actually worked with him on some of the text, and after he built it and published it, and he sent me a print circuit board to build his balun, and after he had published it, he decided he liked my balun better, so he has redone it, reworked it with my balun practically, and then he moved QTHs and was able to put up a normal OCFD. So he replaced his EC OCFD with a normal OCFD using my balance. So gibt es noch mal Fragen da aus Deutschland?
Not really. I'm absolutely flabbergasted.
Well, great.
What's very interesting, but I have to let it go down to my heart first.
Yeah.
This will take several hours, I'm afraid.
Well, for you, I'm going to talk in English. For you, I would recommend this book. I can't get the camera to show these things. I have to turn off my. Well, you may be familiar with it. So Karl-Heinz Hiller, DL1 VU. Yeah, he wrote this book 20 years ago, and it's available from Funkamateur, usually for between €3 to €5. And that's where I learned an awful lot. But the problem was he didn't go far enough. And so I read this book. He talked about more things to do. I recommended earlier when you're researching balance that you read the article from W7EL. And he did a lot of tests for common mode current and so forth. And he ended his article by saying, once he's completed it, he learned so many more things there are still to be tested and tried and all that. So I just went through and I made a list, and I put that on my to-do list. I'm going to test and try what he says is left outstanding to do. And of course, I didn't feel at all competent enough to do that alone, but I have good friends. In fact, almost all of my friends are good engineers. I was not. I was a marketing guy, and they're all good engineers. DJ1AT, he wrote the textbook for all the universities on antennas. He's my best friend in life, and he helped me a lot. But as did Steve, and then GM3, SEK indirectly. I never had direct contact with him. And man, these guys really taught me and helped me to do it right. And so, including calibrating the instruments before I used them, etc. And so then I went through and I started measuring all these things that other guys had said need to be measured. And I came up with results, and they're all published on my web. And anybody that wants to dispute them, they're welcome to read the measured data, try it themselves, and we'll compare data. But I'll guarantee you, you'll read a lot of nonsense in textbooks.
I'm sure about that. Yeah, but Karl-Heinz Hille is he's quite famous. We've known a lot of articles of his in SecureDL, I think, for example, and other publications as well. He was quite famous for his travels, always taking an arrow and a bow with him to shoot out his antennas from hotel rooms into palms nearby.
I know. What did he published? What, 200,000 QSOs or something from the Far East? Or yeah, I mean, I followed him. Well, I had a lot of nice talks with him too. You know, I mean, he's silent key now, but he would always, you know, I worked for Spiderbeam for 15 years. I retired 3 years ago. So in Friedrichshafen, he would always stop by the booth, you know, and have a chat with us. Great guy.
Yeah, that's right. Will you be at Friedrichshafen Radio?
No, we like, you know, I would still go if Spiderbeam went, but Spiderbeam is not going. Vimo is not going. Defona is not going. Kenwood is not going. It's dying.
No, pity.
You know, yeah. So I really, you know, with Corona, I'm 75 years old, a little bit overweight and all that. It's not a great idea to be around thousands of people. You know, it's I don't mind the smaller groups. I mean, presenting like this, I've never done it before. It's kind of strange because I have dead silence on my end.
Yeah.
And I say, you know, ground control to Major Tom, anybody out there? You know, I can see your pictures, but, you know, it's quite different when you're giving a live presentation where you can see the faces and so forth. And sometimes if I saw somebody with a really puzzled look, then I, you know, would, hey, you know, was that not clear? Maybe I should explain it a different way or something. But on the other hand, this is a lot cheaper than flying over to the UK.
Yeah.
That's for sure.
I would like to. I'd like to fly to the UK, but when there's WPX contest, the prefix contest, because there is not very many G5s of us left anymore.
No, that is true.
Or even G3s. I only know Peter Waters, I think.
Yeah, yeah, and he's getting up there in age too.
Yeah.
We've got our Mike. We've got our own G3 SDY in the club, of course. So
yeah, that's correct. That's right. That's right.
Yeah,
Roger,
but
Roger, you had your hand up.
Where's Roger? Oh, hi, Roger.
Hi, Rick. Thanks for that. They're really interesting. Yeah, like others have said, there's a lot to digest there. I wonder if you could expand a little on how you measure the common mode current. I think you said a clamp meter, but my clamp meter will measure hertz, kilohertz maybe, but not into the megahertz. I just wonder how you get that accuracy.
You know, the best way to do that is to show you, but I'm just, if Nick can help me to turn off my presentation, and if I can hit my website, you can see it. And there are the, okay, now
the presentation's off. You'll need to go back into.
Can I
share your website? Yeah.
Let's see if I hit this. I can't. Now, if I disappear, I'll log back in again. I'll dump that. No, leave meeting. No, I don't want to do that. Okay, yeah, here, down here, I can see it. Let me move this up here and go to.
Share screen.
Yeah. Bear with me a second. It's coming up. So CMC. Okay, so I've got that. Now I just have to, well, I've found it on my screen. I've got to get it back up so you guys can see it.
You've got to hit share screen and then select the one you're looking at, Rick.
Yeah, but I've lost it again. Oh boy. Sorry, guys. Okay, it's this one. And now, see, I've lost the menu for share screen. So maybe this wasn't such a good idea. Okay, here we go. I hit share screen. There it is. Share. Well, I still see the same old one. Oh no, this one is there. Can you see it?
Yes.
Yeah, we can. Yeah.
Okay, so now there's about half a dozen circuits floating around where you can build your own real cheap. But you know, I was in a hurry and I wanted to be sure I had good instruments, so I bought this. Actually, kind of a half truth, because I convinced Spiderbeam that they needed to buy that for me because I was developing antennas that they might want to sell, and so they bought it for me. And it looks a bit funny here. I've got this little one piece of coax on here. It's about 10 inches long, something like that. The problem with these clamp-on meters is the diameter is big enough for RG2. What was it? RG11, I think, was even thicker than RG213. And then when you're measuring thinner coax, what I noticed was the reading on the scale would vary because you could push the clamp around closer or farther away from the coax. So I was getting different readings. And, you know, you can't use that when you're going to be comparing balance. So I said, okay, I'll take RG213. I wrapped a couple of layers of tape around it so that I had a tight fit of the clamp. So then it can't move. And then what I did was I just inserted this every time I wanted to measure somewhere. So I always had the meter clamped exactly with the same tight fit, regardless of what balun I was measuring or what length of coax I was measuring, etc. Because otherwise that would it'd be one more variable that comes into it. You know, you wouldn't know for sure. And the whole idea was not to come up with the best antenna. I was trying to understand how common mode current affects OCFD antennas, but I began with the 40-meter dipole, and all the tests I ran on all of the antennas, I also ran on a 40-meter dipole, and that was my stake in the ground. And once I had that, I could see just how good or how bad of a job the baluns were doing. And then I would take sometimes another choke and add it to the baluns and see what happened and so forth. And I made altogether 1,000 measurements, and it's actually 500 pairs of measurements, because I would measure with an analyzer and with the RFM meter, and then I recorded them in pairs. So you could see the amount of current, or common mode current, but you could also see what it was doing to your antenna.
Right. So that's a multi-turn whatever clamp meter.
Yeah, inside there,
just around the outside of the coax.
Excuse me. Yeah, it clamps over the coax, but inside this, it's just like a big toroid that's cut in half. There's a number of wires in there, but I haven't looked inside there for 6 years or 5 years, something. So no, wait, that's been, that's been 10 years. I haven't opened it for 10 years. It's just always clamped onto that thing, but there's a number of turns going around there. There are plenty of, G3, what was it called? TXQ. He has somewhere on his website instructions for building one. GM3 SEK has it. VK1OD has it. W8JI has it on his website, and they're all similar. So there's lots of them floating around, They're cheap to build. I think I paid about $100 for this. Last time I checked, they weren't, due to Corona, a lot of stuff wasn't available, but they might be available again. But, they had a cheaper one. If I had to do it all over, I would have bought the cheaper one. The advantage of this one is it has 2 very low scales that are amplified. So it can measure very low current, RF current. It's useless. And the reason it's useless is when you clamp it onto an antenna and you have it on those low scales and you're not applying any power to your antenna, the meter is wiggling all over the place between half scale and full scale and back and forth. There's so much RF floating in the air from who knows what. I don't even live in a city. I live out in the country, but there's just so much RF in the air. And then I have to go to the lowest scale that's not amplified. Well, the cheaper meter can measure down to that level as well. So I may have just bought the cheaper meter. They have 2 of them. Vimo sells them here. Probably others do too, but I think I got mine from Vimo. So it's like 10 years ago, so I don't remember exactly.
Yeah, Roger Waters and Stanton sell that MFJ RF current meter about
Okay,
200,
yeah.
about £200 they are.
No, I wasn't interested in buying one. I was just wondering how you do it
Oh
because
yeah,
yeah, you're ordering a multimeter or whatever will work. Ordinary transformers will be saturated at megahertz rate.
I could show you quite easily if I were better at using this Zoom, because one of my friends in Italy sent me a diagram today, and he'd come across it. He wasn't aware that something like that existed. He thought he was showing me something new and great, and there's a schematic of it and a picture of it. It's in one of my emails, but I'm afraid if I try to get it, I won't be back for 5 minutes. It takes me so long to navigate this stuff.
No, it's just I've not come across that before as a specific instrument, but no, that's interesting. Thank you.
Well, okay, then you mean my specific one? It's just called an RF ammeter, and there are other companies building them too. Let me just make a note, because I'll look up some of these.
Yeah, Rick, I've just put in the chat a link to G3TXQ Steve's article in Radcom in 2015 on
that's good, and then everybody can access that.
Common mode current and chokes and measurements as well.
Okay, yeah, well, because like I said,
there's an appendix in his article there on how to measure common mode choke impedance.
Yeah, and there's 3 or 4, so but that's probably the best, because I assume everyone can access that. So otherwise, pop me an email and I'll hunt up a couple of the ones and send you a link where you can read it on their respective websites.
Right, thanks very much. Thank you.
Thank you, Roger. Richard, got a question for you, and then I think we'll call questions to a halt. Go on, Richard.
Yeah, good evening, Rick. Nice to meet you again.
Hi.
I've just looked in my drawer. You probably can't see what this is. It's one of your little insulators and two bits of cable that you gave me, I think, at Newark. And I think you were looking for a different wire manufacturer at that time.
We were. I now I can, every now and then it pops into view and then it disappears again. So yeah, and we were. You guys won't believe. I'm glad I don't have those headaches anymore. In the lightweight and ultra lightweight antennas that Spiderbeam was building, you can't believe how many times we changed the wire, because the wire manufacturers kept going out of business, or they would be selling out or merging with others, and then they'd change their product or discontinue, and then we'd keep changing, and then we'd build a say 50 or 100 antennas. And then they'd change it again. And every time they change it, even if you had the same part number for the wire, it wasn't quite the same. And so you'd build the antenna, and the SWR curves would be off a little bit. So every time, and it got to the point, even if we ordered from the same vendor, and for the longest time we were ordering from Wireman, then we were ordering from DXWire, both of those changed a couple of times. Spiderbeam is now ordering from Davis RF in the States, Polystealth 22. In my opinion, this is the best wire that we've ever used for the lightweight stuff. But every time you change the wire, I would have to redefine the dimensions for the boys that are building the antennas. It's changed just a few centimeters, but if you don't adjust it, the SWR curves aren't where they need to be. And the same thing happened to us with the thicker wire and with the coax. It's unbelievable. If you're not involved in the manufacturing end of it, it's hard to believe that happens. Wire is wire and coax is coax. It's not. And every time, for me, building an antenna, tuning the antenna, you're talking about a week to 2 weeks of work for one antenna. And if they change the thin wire, well, I've got 3 different antennas that use it, so I've got a couple of months of work just so Spiderbeam can start production again. And by the way, they don't have anybody else that does that. They still, I still have to help them on a few things. I don't work daily for them, but for stuff like that, and it doesn't happen often, but every second year I've got to do that.
Yeah, brilliant. Yeah, I use the 404 for portable work. Sat in the car.
Yeah.
The only thing that I find after transmitting for a while, I just sometimes get a little bit of screen flicker, but that's all. The SWR never changes.
Yeah, then I mean, you could try putting just this Maxwell choke. This camera never works, but if you just put that right between the the transceiver and the antenna. That would probably solve it.
Well, you probably don't remember, you made me a little one on a toroid.
Ah, yeah. Now I do exactly, Richard. Yeah. Right.
Yeah.
Okay.
And that one, the coax broke, so I just bought a big toroid and I just wind, the end
That's
of
fine, just fine. You don't have to
to.
cross wind or anything. They could be wound in one direction, but that should cure that flickering. It doesn't happen often. We've sold over. I say we. I'm not with Spiderbeam anymore. I'm retired. I'm a civilian, but we have sold over 2,000 of those antennas, and 2 times we had to add a choke, and you were the lucky winner of one of the times. So you were, 1 out of 1,000. It's you. So I just wanted to say something, and now we're going to talk about links. Of course, I'll repeat this next time, but people are always asking me, how long do we cut the antenna? And I said, well, the answer is not in feet and inches nor meters and centimeters. The answer to that is in megahertz and kilohertz. You cut it to be, well, here you go with resonance, not resonant, SWR minimum for a certain frequency, and you begin there. And the reason is, if you use a different wire, it's a different length. But cutting for that frequency is always the same. So you want it electrically to be at a starting frequency. And I can tell you a ballpark number, but you better be willing to make it 20 centimeters longer or shorter, maybe even more, because it depends on the wire. And I've never worked with, in the last 50 years, I've never used bare wire. I've always used insulated. I don't know how it might affect it if you use bare wire, but it's certainly going to change. But it's not going to change. My principle is not going to change as long as you're tuning by, looking at frequency and SWR and stuff like that. That'll work even regardless of what wire you use.
Yeah, the other thing that changes, obviously, when you're out portable, sometimes you get your portable mast up 5 meters, 10 meters. The angles are different, and it does vary it a little bit, but by and large, it's been brilliant.
Yeah, well, the funny thing is, when I got into this OCFD stuff, I didn't build these for Spiderbeam. I built them for me. I love portable operations, and I've always been a fan of wire antennas and field days and, motorbiking and going to mountaintops and to Isle of Man and stuff like that. And when I built the antenna, Cornelius, the owner and founder of Spiderbeam in Germany, he said, hey, we can sell that. And he asked me if I would mind if they sell it. I said, hey, go ahead, knock yourself out. Of course, mine was on a open frame backplane. And he said, well, we can't sell that. That looks too homemade. We've got to put it in a case. You won't believe it. It took us 6 months to find a case and get production started. The antenna was finished, but because of a 3 quid or even less, probably a 2 quid plastic box, took us 6 months delay of the production. But, you got to first find one. And we ordered several that we didn't like, and they would always send us 2 or 3, but you'd have to buy a couple hundred once you decided you wanted it, and then you start building them, and then here comes the next bit. So we hired a guy to build the antennas. So once we were ready to go, he broke his hand or wrist or something like that. He couldn't do it, and Friedrichshafen was coming up, and there was nobody to build them. So I built the first 35 antennas myself, and I didn't want anything to do with building them. I just designed them. And so fast forward 3 or 4 more years, I designed the 807 antenna because, well, I'd already had, it wasn't so difficult. I already had one of my own up, but I changed the feed point. I like the 29.7 better than the 20%. So I designed that. It was ready to go. Same guy was going to build them again. We ordered all the parts. He broke his foot. So I built the first 30 807 antennas. And Spiderbeam didn't pay me for that. I just had to build them. But on the other hand, they treat me nice. If I need a new pole or something, they send me one.
Excellent. Thank you, Richard. And thank you, Rick. Look, everyone, I think we're just going to call it a day for the recording this presentation from Rick. I think it was absolutely superb. And I think, Mike, you were absolutely right. You need to have a look at the notes with the handouts and follow some of the links and have a think about it to follow it if you want to look a bit deeper into it. But the information is all there. I mean, that Rick has done a fantastic job in the last, well, I think 12 months, Rick. That
we've been working on this for a year. Yeah,
we've been working on this for a year, and Rick's done a fabulous job of condensing so much information and putting the links into the handout. So congratulations to Rick. Can we show our appreciation to Rick for the talk tonight? Absolutely brilliant. Thank you, Rick.
Well, thank you guys for staying with me. It's pretty dry. I think the second part will be more fun, you know, when we see how to build them. Okay, so second part is in June, and we'll send out information to remind people of that. So thank you as well to our viewers on YouTube. So I'm going to hit the record button to stop. I wish everyone a good night. One question for, or one comment first. 7th of June is my presentation. Please do not put Emil on one day before me. Yeah, that was Rick. That wasn't the intention originally. That was a special request from Emil. Yeah. This was the only night he was free to do it. Yeah, he still works. I mean, after all, you know, I collect retirement, so he's paying my salary. Good night, guys. Yeah, cheers. Adriana,
Good night. Thank you.
Who's gonna be